Okay, so let's start. So last week we were talking about consistency. I gave several definitions of consistency models, starting from strict consistency all the way to eventual consistency. And towards the end, we were talking a little bit more about the implementation rather than the definitions. And I presented this notion of epidemic protocols for eventual consistency. Now, what I'll do today is give a very high level overview of how some of these techniques are implemented. This is still at a very high level. We will not go into the details of how you implement a specific consistency guarantee. That we will come to when we look at certain systems like the web and file systems and so on, and see how to implement those in specific context rather than a more abstract discussion. So this is as I said, a high-level discussion of how to go about implementing any consistency technique. And we'll see that there are two types of implementations techniques. One is based on the notion of a primary and the other one is replicated, right? So the first case, you have a primary replica that is responsible for maintaining consistency. And then there are other replicas that will talk to the primary. Okay, so often in databases, this is referred to as master-slave. There's a master, which is called a primary, and then there are slaves. They are all replicas, but one replica is more distinguished than the rest. So it takes responsibility or charge for determining how to implement any particular consistency mechanism. Okay, so those are primary-based techniques, and we'll see two flavors of it. The other one is replicated, right, which means that there are several replicas, but all replicas are treated identically, and it's a decentralized approach. So if all replicas that are up will participate in maintaining consistency and determining which is the latest write and things like that. Okay, so we look at both classes of sort of techniques. Okay, the replicated write, the primary based, you'll see two variants. One is called remote write and the other is local write. So this picture looks fairly complicated, but it is actually quite straightforward. So we'll assume that there are many replicas and there is one node here that is the primary for a certain data item. Now across multiple data items, different nodes may be primary. Doesn't mean that one node is primary for all of the data. You can even distribute the responsibility for a primary, but for data item X, it could be a file, it could be a record. This node is the primary. So what happens in remote write, as the name suggests, very straightforward approach. Whenever any client, okay, which are shown in those boxes at the top, wants to perform a write, it is going to send the write to its local replica, which is then going to forward it to the master, or the primary. That's what is shown here. Write comes in, W1, it's forwarded to the master copy. Master copy is updated, and an acknowledgement is sent back. And then it's the job of the primary to implement any consistency technique. Okay? It can then tell the other replicas saying here is the latest version of the data item. It could send what are referred to as invalidate messages saying I have a newer version. So if you have any copy, throw it away. Any of these techniques could then be implemented at the primary. Okay? Read works the same way. Okay? Unless caching is used, whenever a read request hits a replica, it's sent to the primary. Okay, or if you have cached or replicated copies, then you will just reply using a local version. Okay. So this is referred to as remote write. Now we will see that most file systems use this approach, which is why you have a file server and clients in any distributed file system. There will be a primary which will take charge of maintaining a master copy of a file as well as maintaining consistency of any replicas that are at either clients or other servers in the system. Because the file systems use this approach quite a bit. So this slide simply shows after write is performed that the write request is propagated to all of the other replicas. Okay, so write comes in W1, it is sent to the primary. Okay, the primary is going to send an acknowledgement W3, and then all of the write requests are sent to all of the replicas. This is the consistent. Now, when is it sent? How is it sent? That depends on what consistency guarantees you want to provide. That I'm not discussing here. That's a separate issue. This is simply at a high level how you can implement consistency using a primary copy and doing remote write. Okay. The other way to do this using a primary is what are referred to as local writes. So here you want to perform writes locally to improve performance. Okay, remote writes are going to incur overhead. Every write request is sent off to a remote node, which is the primary for that node for updating as well as consistency. Okay. Now, what if you wanted to improve performance and have all of the writes be local? Okay, so the way this is done is the first time a write comes in, okay, it comes to a local replica here, that's step 1. The local replica asks who is the primary for this data item. In this case, it is this node here. And it basically sends a message to that node saying, delegate the responsibility of primary to me. I am going to be the new primary. Okay, in this case, and that node says, fine, you can be the primary, I'll be a slave. Okay? So then the responsibility for becoming the primary is transferred to that other node. At this point, this node becomes the primary for the data item, so all subsequent writes are local. Okay, this is simply a performance optimization. Okay? You basically, rather than sending writes to a remote machine, you basically take over responsibility for the primary and all writes are then local. Okay? Again, this is used in many different file systems. When we talk about network file system NFS, specifically NFS version 4 has this notion built in. Okay? In NFS version 4, the server for a file can keep changing, the primary server. You can actually delegate responsibility and have some other nodes become primaries for certain periods of time. Okay, this is mostly done as a performance optimization because for writing to a local disk is going to be faster than sending the write to over a network to a remote machine and have that perform the write. Okay, so that's the reason for doing this. Now, this performance is better, but you have to keep track of, because the primary keeps changing. You need to have additional techniques that keep track of who is the current primary. Okay? You can't use some static scheme like you hash and file name and it tells you the primary, and you don't need to keep additional info. Here you need to have a separate metadata to track the primary for each data item. Okay? As far as once a write comes in, what happens to that write, how it's propagated is exactly the same as remote write protocol. Okay, now this node has become the primary. Okay, there are lots of arrows here, but all that they are showing is when a write comes in, you perform the write locally and you send it to the other replicas, all the slaves, because that's why that write is being broadcast to all of the other nodes in step W4. Okay, so that's all you need to do. Same as a remote write protocol. Okay. So when we come back to NFS, we look at specific implementation of both remote writes and local writes, okay, as well as other distributed file systems. Now let's talk about a more decentralized approach for consistency maintenance. So in this case, again, there are a number of replicas for each data item. Okay, it's a distributed data store, but there are no primaries and secondaries. There's no master or slave. All nodes are treated identically. All replicas are treated identically. Okay? So no primary, any replica can service reads or write requests. So in this case, you have to ask the question, how can you ensure consistency? Okay? Who takes responsibility for telling all the other nodes? And when a read comes in, how do you figure out what is the most recent version of the data item? Okay? So the way you have to go about doing this is you have to basically use this notion of voting, okay, to figure out what is the most recent version of a data item. Okay? When a write comes in, you have to decide how many replicas to send it to. Okay? When a read comes in, you have to figure out who has the most recent version. Okay? And all of this is achieved through this notion of voting. Okay? And this entire class of protocol, this is not one, I'm going to present the simplest version of this protocol. Okay? But this entire class of protocols is referred to as quorum-based protocol. Okay? So you need to have a quorum. Quorum says you need a majority vote. That's what a quorum means. Okay? So essentially what we are going to do is we are going to use the notion of voting to perform reads or writes. Yeah, and I'm going to present a little bit of terminology, give some examples, and then we'll come back and examine this properties of how you achieve majority vote and so. So let n be the number of servers or replicas in your system. Okay? So we will basically have two kinds of groups for voting. A group that votes for writes and a group that votes for reads. So we'll call this a read quorum and a write quorum. So NR stands for a read quorum and NW stands for a write quorum. Okay? So if you have n nodes in all, you can define the write quorum, or the write quorum is defined to be a strict majority. Okay? So the number of nodes that have to agree on a write request has to be at least half the number of nodes in your system. Okay? For consistency, we'll see why all of this is necessary, but this is a very simple quorum-based protocol. So write quorum requires a majority. Okay? Now, if you have NW defined to be a write quorum, okay, then NR can be set to any value such that NR plus NW exceeds strictly greater than N. Okay? So what that means is to perform a read, you need to poll at least NR's replicas and say what is the most recent version of the file you have. If they all return the most recent version ID and they all match, then you can basically return that and you're guaranteed that's the latest copy. Okay? Why that is the case, we'll see that in a moment. Okay? So let's look at some examples of this read and write quorum here. Okay? So here we have 12 nodes, okay? A through L. Okay? 3 different examples of this majority voting protocol where you set different sizes for the read and write quorum. In this case, we set the write quorum to be 10. Okay, 10 is a strict majority. You need at least 7. Okay, but you basically configure the protocols. And whenever you perform a write, contact 10 nodes at random and send them this write request. Okay, you can pick any 10. It doesn't matter which 10 you pick. You pick 10 at random. Whoever receives the write picks 10 nodes at random and sends them the write request. So they have the most up-to-date version. Okay, and read quorum is set to 3. And you can see NR plus NW is 13, which is greater than 12. So it meets the properties I had, these 2 properties we just talked about. Here N is 12, so NW is, we set that to 10, it's greater than 12, so that condition is met. And the sum of this becomes 13 because we set the read quorum to be 3. Okay? So now the question is there a way to perform a read request where you get an out-of-date version of the file? Okay? So the way reads are performed is read comes in, okay? You pick 3 nodes at random, okay? And you ask them what is the most recent version of the file you have. Maybe you have timestamp. Let's simply say you have a version ID. Every time you write to a file, you increment the version. Okay? Same can be achieved by using timestamps, but let's forget about timestamp. That's every write increments the version number of the file. So the question is there any way for this protocol to query 3 nodes at random in the read quorum and have these 3 nodes agree on an outdated version of the file? Okay, if so, then you will sometimes return outdated version. If there's no way to do that, then you will always return the right version of the file, the most recent version of the file. Okay. So here is an example that is shown to you. So in this case, the dotted lines show you the write quorum. So the most recent write, you pick those 10 nodes that are in that dotted box. Okay. Now, after that write is performed, the read request has come in. Okay. The node that received the read request picks A, B, and C as the servers to query and ask them what's the most recent version of the file you have. Okay. They all have to agree. Okay. If they all agree, then you are guaranteed is the most recent version. And the point is because NR plus NW is greater than 12, the read quorum and the write quorum will have to overlap. There will have to be at least one node that will overlap. So there is never a way you can get them to agree on an outdated version. So in particular, A and B did not see the most recent write because the most recent write was sent from to servers C through L. Okay, that's the dotted box. So A and B still have the old version. So when you query them, they will return your old version ID. Okay, but because the read quorum is 3, you have to query a third server, which has to be necessarily one from the write quorum. That's why NR plus NW is greater than 12. So you have to guarantee an overlap, otherwise you will get an inconsistent result. Okay? So as a result, C will not agree with A and B. Okay, so that poll will fail. You will not get a agreement. Okay, so you will try again. You will pick 3 other servers at random and say, what's the most recent version of the file? Okay, eventually you will pick 3 servers from this pool, okay, the write pool. At that point, they will agree, okay, because they all have seen the most recent write, and then you will basically be able to return the most recent version. Okay. So what this is showing you is by simply voting, you can ensure that you never return outdated versions of the file so long as you meet those properties. Yes, question.
In this solution, does fragmentation become a problem?
Fragmentation?
Like, say, like DH and L, like they have like the newest copies of the file, and then E and I have different kind of like slightly older copies and so on.
Okay, so question is, can you have issues where some nodes have more recent version, some nodes have older version? Is that your question?
Yeah.
So that could well happen. Okay, so it's not guaranteed that in this, if you configure it this way, it's not guaranteed all the nodes will receive the write. Okay, but you will ensure that you will never return outdated version of the file. Some nodes may have outdated data, but a read request will always return the most recent version because of the way we set the read code. Okay. Here is another example. Okay, we'll see a different property holds here. Here we have set NW to be 6 nodes. Okay. NR is set to 7 nodes. Okay. So in this case, let's say the dotted line is where you performed a write. Okay. So that's basically nodes D, H, L, I, J, K. Okay. Now read quorum is 7 nodes. So you have to pick any 7 nodes at random. Okay. And basically have them agree. So in this case, the read is sent through A, B, C, E, F, G, which have not seen the write, and it's also sent to H. So you will see again in this case, the read will not succeed because you always have to pick at least one of these nodes. Okay. So you will these nodes will disagree with that node in terms of what is the most recent version. So you will never return any outdated version. But there's also a problem with the way we have defined these numbers. Okay. Anybody figure out what the problem is? Okay. So NR is greater than NW, so they are never going to agree. There's no way to pick 7 nodes here such that you will actually ever have agreement, because if you pick these 6 nodes, then you'll pick 1 node from the other set. Okay. That node would not have seen the write. Now why did this happen? Because we said NW has to be strict majority, so it should have been greater than 6. We picked it to be 6. So we have not violated safety, but we have violated what's called liveness. Okay, liveness means something good happens. Safety property means nothing bad happens. So we assume that nothing bad happens in terms of returning outdated result. But we don't have liveness because there's always, reads will never succeed in this scenario. Okay. In particular, if you had set NR to 6, reads could have succeeded if you have A, B, C, E, F, G, but that returns an outdated version of the file. Okay. But we'll say that's not correct because NR plus NW in that case is 6 plus 6. It adds up to 12, and we said we need it to be greater than N, not greater than or equal to. Okay. Which is why those properties are important. You have to meet those properties in order for you to do whatever or achieve your results. Okay. The last scenario is one where you pick the write quorum to be the entire set. Every write goes to all the replicas. In this case, the read quorum can be simply set to 1, meaning you don't have to poll anyone. Okay, you just, all reads are local. Whatever replica they hit is guaranteed to have the latest version of the file. Okay, this is referred to as read once, write on. Okay, you write to all, but then you can read from anyone. You don't have to ask it. So you can pick any values of NR and NW depending on what you're trying to achieve, so long as the properties here for the read quorum and write quorum are achieved. You can simply use voting to make sure you all agree, and then bad things won't happen. Okay, but the protocol will have different overheads in terms of reads and writes. So in particular, here reads are local. You don't need to ever send a message to a different machine. Writes require you to propagate the write to all the machines. So this is also referred to Gifford's quorum-based protocol, named after the author of the paper who proposed this protocol. There are many different flavors of quorum protocols. Okay? They all require voting, okay? And you have to agree on the results of the vote. Okay? Not even majority. In this case, you actually have to agree. Okay? And by simply setting the write and reads quorum to be of certain sizes, you can ensure that no primary is necessary. There's no, it's a completely decentralized approach. Okay, somewhat randomized as well. You can pick for your read quorum any random number of servers that equal to the size of the read quorum. Ask them what is the most recent version. If they agree, you can safely return that version to be the most recent version and not have inconsistent results. Okay. There is higher overhead than simply having a master. Okay. The previous two protocols, which are primary based, did not have there's no overhead of voting and things like that. Okay, but here, because you did away with the master, you have to involve all the replicas in determining what is the, not all, but all the ones in a read or a write quorum and determining what's the most recent version. Okay. This is the first time we have encountered a voting based protocol. We did that a little bit in leader election. As we go on, when we talk about fault tolerance, we will encounter voting and agreement and all of these techniques more and more, and we'll eventually end with Paxos, which is also a technique that requires agreement and voting and so on. Okay. This protocol assumes there are no failures, which is why the voting is straightforward. If there are failures and you pick nodes in the presence of failures, then the protocol may not work. And that's something to keep in mind. Any questions on this? Okay. So that's basically the end of the discussion on replication. I just have a few quick thoughts and then we'll move on to fault tolerance. So we have looked at a whole slew of definitions of consistency guarantees last time. And we talked about two kinds of implementation techniques. One was epidemic protocols, okay, implementing protocols that provide eventual consistency. And what I presented today was either primary based protocols or quorum based protocols that allow you to implement different forms of consistency. Okay. Now there are systems that use some of these ideas in practice. We will encounter them, as I said, when we go along and talk about the web and file systems. Okay, there are several techniques we did not discuss at all in replication. Okay, first is where do you place the replicas? Okay. If you have geographically distributed workloads, the placement of replicas can have a significant impact on performance, just as the consistency protocol also has a significant impact on performance. We'll come back to that when we talk about the web. Okay. The other question is the number of replicas permanent? Is it temporary? Does it vary over time? Okay. Very important problem. Okay. In many of these cases, we have assumed that the number of replicas is actually fixed. Okay. There are many systems today that can dynamically vary the number of replicas based on the workload. Okay. As the workload increases, the number of replicas is also increased so that you can scale the total capacity. Okay. Many cloud-based platforms provide this automatic technique where you can have a web server. Okay. If it sees that the load on the web server goes above a certain value, the system will create new copies of the web server, new servers that will allow you to run additional replicas of your website automatically. Okay. No user intervention is needed. In this case, the number of replicas is varying over time. Okay. As the workload subsides, the number of replicas is reduced. So the pool of replicas may itself change over time. Okay. How do you deal with consistency when you have variable number of replica? All that, those are interesting questions. We have just glossed over all of those. Okay. And then there is this whole issue of using proxies or caches. Okay. Replicas, I mentioned replication and caching are related techniques. Both allow you to keep multiple copies of data items for either caching is typically done for performance reasons. Replication itself could be done for performance or fault tolerance reasons. And when we come back to caching and content distribution networks, we will look at all of these protocols and consistency techniques. How do you provide strong consistency? How do you provide weaker forms of consistency? All of that discussion we have deferred. Okay, that's going to come back. We'll come back to it in chapter 12. Okay. So we've done a basic version of replication, and now we'll come back to it as we do the case studies later. So the discussion is not done, but for purposes of today's class, it's done. Okay, so I'm going to switch gears and talk about fault tolerance. Okay, so we are done with replication. The other end, sort of side of why you want to replicate is to deal with failures, and that's what we will discuss. So today I'm going to give a quick overview of why you need to deal with faults in distributed systems, okay, why and how you can go about doing that, and then we'll talk a little bit about Byzantine faults and the Byzantine general problem. Next time we are going to talk about trying to reach agreement in the presence of fault. We'll talk about distributed commit. We may get to Paxos next time or the week after. Okay. So let's start with fault tolerance. Okay, so it should be clear that in the distributed systems, you have first of all the ability to deal with faults if you build your system right. If you have a single machine or a centralized system, that machine fails, application is down. There's nothing you can do about it. in a distributed system, since there are multiple independent nodes, if some subset of nodes fail, let's say one node fails, okay, it is possible for the other nodes to take over its responsibility and the application continues to run. Okay? That's an advantage you have in a distributed system, just from the fact that you have multiple components. Okay, some components may fail, others may not. Okay? Now, so this is an advantage, but what the advantage is also something that gives a limitation or a disadvantage, which is the complexity of your system is going to go up, because you have to implement a fault tolerance technique into the system. In fact, the larger the system, the probability that some nodes are fail keeps going up. Okay? And in very large system, there is some subset of nodes will always be down at any given time. In fact, that will be a common scenario, not an uncommon case. As a result, fault tolerance is necessary. It's not something that is desirable, it just becomes necessary. Okay, we'll assume here that nodes fail independently. Okay? If nodes fail independently, the probability of a failure is the probability that any one component fails, which is the probability of one minus the probability of no component fail. P is the probability with which any component fails. Okay, as the number of nodes goes to infinite as 1 minus p to the power n. Okay? So this term starts going to 0 in the limit. Okay? So the probability that some components are fails starts going to 1 as the number of nodes keeps increasing. Okay? Which is why I said in very large systems, some nodes are always down for one reason or another. Okay? If you take any very large system, let's say Google search engine or any such very large distributed system, which has tens of thousands of nodes, a few hundred nodes will always be down. Either they have failed, they are down for maintenance or any such reason. And you don't want the system to stop. Okay? You don't see the system has stopped functioning because some nodes are down. Yes, question.
So just to clarify, the probability that any given system still has the same P. If you're just talking about the probability that there is even one system that happens to be down as n goes to infinity.
Yes. So let's use proper terms. So there are number of nodes in a distributed system. Right? So we assume that there are n in a given system. Okay? P is the probability that a node is up. Okay.
Right.
So this is the probability that some node in the system is down. That could be one node, one
Right,
or many.
Yeah, that increases, but P itself stays the same.
P itself stays the same. Okay, but since this is a number that's less than 1, as n goes to infinity, P to the power n is going to go to 0. Okay, so this expression is going to go to 1. So P is not going to change for a given node, but for the system as a whole, the probability that any component is down is going to keep increasing. That's the point I was trying to make. Yes.
A follow up on that. So why are we singling out on the node? Because in a distributed system, network is a very critical component of it. So if a critical part of network fails, then you're just bunch of nodes would go away. So in those scenarios, are you going to put n as a large number and take care of that? Is that handled differently?
So you are saying in a distributed system, the network may itself fail. So that may cause partitions and nodes may fail. So you can assume that the routers are part of the distributed system. It doesn't matter. You can have actual nodes and network elements as being part of that system. And P could be the probability that any of them fail. Okay, if they fail, then they can cause a network partition. As a result, the system will experience a failure as well. Okay. So I'm not following what you asked in relation to that. What was your question?
Is this model very simplistic, or is it robust enough to consider all the failure scenarios?
Okay. So this is so first of all, this is not a very sophisticated model. It was simply trying to argue that when you have large number of components in your system, okay, failures become the common case. If you have 2-node system, a failure may be an abnormal case. It may happen once in a while. Most of the time, both nodes are up. Okay, if you have 2,000 nodes, some fraction of some nodes being down, even when there are independent failure, will start approaching 1 because they fail independently, and this expression simply goes to. That's all it was saying. So it was not trying to actually model network failures or anything like that, although you could put that into the model. So the meta point here was distributed systems can deal with failures because they have independent nodes. But as the system size goes, they have to deal with failures. Otherwise, your system will not function. That was the point that was trying. So in other words, incorporating fault tolerance becomes necessary as the size of your system grows, because something is going to go wrong given independent failures. And as a result, you need other nodes to take over those responsibilities. Right? Now take that as one perspective. And here's a different perspective of how we have tended to build computing systems, and which are not at all reliable in some shape or form. People are now used to having your machines be rebooted because something hangs or things like that, okay? Which basically means that you ship software systems that have bugs in them. Okay? You never wait until every bug has been resolved before you ship a software system. Okay? So that's a way of life, because these systems are very complex. They have bugs in them. Okay? As a result, okay, these systems will fail. Okay? They're designed, not designed to fail, but they're designed in a way that bugs are present and they will fail. Okay? Most users, if it's a laptop or a device that you own, are used to occasionally having to reboot your machine, and having the machine sort of come back up, restart, and then it begins to function well. Okay, now contrast that with the not very tech savvy user. Okay, they are accessing the internet, they bought their first smartphone or whatever. They are not used to this mode of operation. When you buy a device, you expect it to work. Okay? You don't buy a television and reboot your television every third day. That's not the way that system is built. It is built for reliability. Okay? Software system or software-based systems are not built for reliability. Okay? Or by definition, because of bugs, they are not reliable. They fail from time to time for a number of different reasons. Okay? So as a result, we are left with components of your system that are inherently not reliable. They have software bugs. Of course, the hardware itself may have bugs. So that brings us back to now you have all these systems that are not built to be reliable to begin with. How do you add a layer of on top for fault tolerance that makes them reliable? Because users that are using them are now the large population of users which are not necessarily tech savvy, and they expect reliability. They are not used to this whole notion of system is down for no good reason. Okay, so they expect that system is always up 24/7. So we have to look at techniques that will take these software systems and make them reliable in some shape or form. And that's the reason we are going to actually look at a variety of different fault tolerance models, some of which will take these kinds of unreliable bugs into account. Okay? So you have to put these two things side by side. Okay? We do not build our applications to be ultra reliable. That's not, reliability is never the first goal often. Neither is security for that matter. It's always performance. Okay? And as a result, we have either unreliable systems that are bugs, or we have less secure systems. Okay? But security and reliability have become very critical, especially in distributed systems, and especially with internet making the systems very widely used by a different population of users who are never used to this mode of operation. Okay? You don't have cars or TVs or any of these other things built in this way. It's practically the only system that is built where you ship a system knowing that there are faults in it. Okay? So with that two sort of contrasting perspective, one, the need for having reliable systems, and the other is we never built them to be that way. Now we have to still try to fix this, okay? Somehow make our systems reliable and dependable. Okay? So we have a need to build dependable systems. So we'll define some terms. Okay? So we'll first term is availability. So availability simply means that the system is available for the functions it's designed to perform at any given time. Right? The way you determine availability is by computing the percentage of time it is available for use. Okay? So in distributed systems, you will hear 5 nines of availability, not reliability. So that basically says that this 99.999% available. So if you translate that into how many minutes of downtime can you incur every year, it is very few. Okay? That means the system needs to be up with such high availability that you can afford to have a downtime of less than a minute per year. That's what 5 nines will do. You can have 4 nines of availability or 3 nines of availability. That allows you to have longer and longer downtimes. Now what that means is this is defined for a system as a whole. Individual components can be down for longer. That is allowed. The system as a whole shouldn't be down for any longer than whatever reliability or availability metric you have designed it to run with. Okay. So this is very hard to achieve in practice. It's very expensive to achieve in practice, but nevertheless, there are systems that are required to perform with that high levels of availability. Let's say a control system that is designed to operate a nuclear reactor. You don't want it to be down. It can cause catastrophic failure. Systems that are designed to control the airplane, you don't want it to be down. Okay? Soon, if you're self-driving cars, you don't want that to happen either. You can't be on a highway, system goes down. You're not even driving the car. That would be bad. Okay, so you want to have very high levels of availability because you have other systems that are really critical that are being driven by computing systems which have not been designed to be reliable. Okay, that's the problem you really need to achieve somehow. Okay, so that's availability. Reliability, system should run continuously without a failure. It's reliable in some shape or form. Okay, safety says even if there are temporary failures, it should not result in a catastrophic failure. Okay, so what that means is individual components can fail, okay, but there is redundancy in the system that other components take over the task. So some components failing doesn't cause a catastrophic failure of the entire system going down. Okay. And then maintainability is sort of not very quantifiable metric, but it basically says a failed system should be easy to repair. And so what that means is once you put a system out in the field, if some components fail, okay, it should be easy to fix that component. You should be able to pull out some part and plug in something else. Okay. That is often unspoken design goals because it's hard to make the system maintainable. But some systems are. You can actually replace parts very easily in the field. Okay. It is not a easy thing to do, but you can design your system to be maintainable as well. Okay. So those are some good goals to shoot for when you talk about fault tolerance. Now we'll talk about different kinds of faults. Okay, so here are three. One is transient fault, intermittent fault, and permanent fault. Okay. So transient fault basically says it's a one-time fault. It comes and it disappears and it never appears again. Okay. It may happen for any number of reasons. Okay. A bit may get flipped in the RAM of a machine for no good reason. Okay. Maybe the small voltage spike, so it flipped a bit. Okay. So whatever integer value was actually stored in that bit has gotten flipped, and then after a while the part begins, that bit starts working well, so that fault never appears again. It is referred to as a transient fault. Okay. Intermittent fault is a transient fault that appears every once in a while and then it disappears. Okay. So it is not going, it's a recurring, somewhat recurring fault, but it's not long lasting. It comes and goes. You can have, the best way to think about this is some problem with your car, some nagging problem that you cannot reproduce when you go to the garage. It makes some noise, but when you start, then I cannot hear any noise. But then you drive off and it does the same thing. So that's an intermittent fault. Hard to track because if you cannot reproduce it, you cannot fix it. So these are all problematic types of fault. Okay, permanent fault is a fault that occurs. It's like a crash. Your system crashed, so you know it has crashed and you can do something about it. Okay, so these are three types of faults that you can actually see in computing system. Okay. So and here are the different kinds of failures that may result as a result of those faults. Okay. So first is a crash failure. Okay, this is very straightforward. Server has just crashed, OS crashed or some component failed, so it just stops. Doesn't work anymore. Okay. Omission failure says a server has failed to respond to incoming requests. Okay. So either it did not process the incoming message or it did not send the message. Okay. That's an omission failure. Okay. Timing failure says a server is responding, but the latency with which it responds is causing an error. It's too slow. Okay. It's causing other things to time out and assume that the server has failed. That's a timing failure. When we talked about streaming media, we had also encountered timing failures. We have video frames don't arrive on time. That's a type of a fault. That's a timing fault. But there are many other kinds of timing faults. You may have a very slow server. Other servers make request of it and then they time out after a while and then they assume it has failed. So response failure says the response is incorrect for whatever reason. You gave a response but the value is wrong. Arbitrary failures are the most complex and hardest kinds of failures to deal with. Okay, they also result in what are called Byzantine faults that we will soon see. Okay, so here the server is working, but it's doing arbitrary things at arbitrary points in time. At some points it's performing well, it produces correct result. At other points it produces garbage. Okay? And then suddenly it starts working well. You don't know why it's doing that, but it has this notion of an what we will also call a Byzantine fault. Okay? It does various different things at different points in time in terms of correctness. Okay? Sometimes it works well, sometimes it doesn't. Okay? So these are the various kinds of faults you can encounter. Okay? In the course of the next 2 or 3 classes, we'll only look at the first one and the last one. Okay? Crash failures are simplest to deal with. Okay? Machine simply goes down. If there's another machine that detects that, it can take over. And we'll see simple techniques to deal with that. Okay? Byzantine faults are the hardest to deal with. First, you need to know that the machine is actually misbehaving, because it's up. It's not that it's gone down. Okay, it is up and functioning, but it's just doing some random things in terms of correctness. Okay, sometimes it works well, sometimes it doesn't. So here you need to first detect it, which is hard, and then you have to isolate it and somehow eliminate its arbitrary behavior from the eventual response. So here is a circuit diagram of how you can design hardware to be resilient to something that's equivalent to either crash failures or even arbitrary failures. It doesn't matter what it is. Okay? And so this is referred to as triple modular redundancy. Okay? So here, so on the top is shown a circuit. Okay, it's a sequential circuit with 3 components, A, B, and C. Okay, this hardware circuit. So you send in an input, A computes a value. Okay, it produces 1 bit, it puts it on the line that input goes into B, it produces an output that goes into component C, and it produces an output. And the output of C is what is the output of your circuit. Okay. Now we want to deal with either A, B, or C failing, or A, B, or C producing arbitrary faults. Okay. The way you do this is you replicate. Okay. So you have 3 versions of A, 3 versions of B, 3 versions of C. Here we are assuming that failures are independent, they are not dependent, and this circuit can tolerate 1 fault of any component. Okay? And the way this works is you feed the same input into A1, A2, A3, you take the output and you vote. If one of them has failed or is producing garbage, the other 2 will override it. Okay? You have a voter here, that's the voter. Okay? So you basically send the output to a voter, the voter picks majority. It picks the 2 out of 3. If one of them disagrees and says that's the output of this stage. You feed that output of the voter into the next stage. Okay, again there is 3 copies of the circuit B. Okay, and you vote again, and so on. Okay. Now the important thing to realize is the voter itself has to be replicated. Because the voter is faulty, these 3 may be functioning right and the voter may simply produce some garbage. Okay, which is why you have 3 copies of the voter itself. Okay, not only is the circuit A replicated, the voter is also replicated, and all the output of all the 3 are fed into each of the voters. So each of them performs the voting step as well. Okay. So if you do this, you can then basically isolate any failure of any component of A, B, or C, or even the voter, and whether they have failed, meaning they simply stopped working, or they are producing arbitrary values regardless of the input. You can still isolate, and you can continue to have the system work without failing as a whole. So this is a very simple idea that has been used in circuit design, hardware circuit design. We will basically use this principles also to deal with software. Okay, we will have redundant software components. We will have voters that will vote, okay, and things like that, okay, to deal with failures. Any questions on this? Okay, these are referred to as TMR, triple modular redundancy, in hardware or circuit design. Okay, so with that in mind, let's now talk about Byzantine faults and simple crash faults and see how to deal with it. Okay. So what we want is basically a property that allows some processes to agree on the result of a computation. So let's say there's a server produces a response to request. So it's performing some computation and producing a response. Okay, so we use the term computation very broadly. We provide an input, the software component does some processing, produces an output. And that's the output of the computation. And we want it to we want the system to produce the right response. Okay? So question is, how do you do this? So you can have, if you have crash failures, okay, this is easy to do. Okay? So in a crash failure, the replica simply goes down. Okay? When it's up, it's producing correct responses, and sometimes it will fail, it produces no response. In this case, just having a redundant copy does the trick. Okay? So if you want to deal with one failure, okay, you basically have two copies. Okay? You basically run the software on two machines. Okay, if any machine is up, it's producing the right result, or if it's down, it's not producing any result, you feed that input to the other. There's no voting needed here, okay, because we're assuming that when the system is up, it is always producing the right response. Okay, it's not producing that. So this is a simple form of failure. These are called crash failures or fail stop failures. Okay? Much easier to deal with, okay, because you are not worried about buggy systems that are producing garbage. You're simply worried about system just stops functioning. Okay, I want the distributed system to continue as a whole, so just have some replicas. Okay, replicas will take over when the system fails. Okay? So in other words, if you want to have K fault tolerance, which means you want to deal with K concurrent failures of any components, you simply need K plus 1 components. You need at least one more than the number that can fail, because that one will be up if K fails simultaneously, and the one that is up is producing right result. Okay, these are simple forms of failures to deal with. Now, as against that, if you have these arbitrary failures, which are referred to as Byzantine failures, okay, this is much harder to deal with. Okay? Here, the machines may be up, okay, but they are sick or buggy. They may produce garbage at some point in time. That's for us a type of a failure, producing incorrect results. Okay? So now we need to deal with Byzantine failures. Okay? So here you can produce erroneous results, random results, malicious results. We don't know what the system is doing, what any component is doing, and how do you deal with it. Even here we will need redundancy, okay? But we'll see that you need far more redundancy than just one extra component. You need more than that, and you need some form of voting to figure out what has happened. Okay? And we'll come back to how do you deal with this. This is just a high-level description of the two kinds of failures and the difference between how to deal with them. Okay? Now, having said that, most real systems only are designed to deal with crash failures, because this happens to be too expensive. I put a question mark on how much redundancy you need. We will see that you need 3 times the number of replicas, okay, than you need here. Okay, instead of K plus 1, we'll need 3K plus 1. Okay. So to have one replica work, you need 4. Okay. So that's a 4x increase in your cost. That's a very high price to pay to deal with Byzantine faults. If you want to deal with it, that's what you will have to do. Okay? As a result, most practical systems take an approach that they will not deal with Byzantine fault, they will only deal with crashes. And if the system performs incorrect results, that's what you have to deal with. Okay? But simply because it's expensive. Now, having said that, there's a lot of research papers on how to deal with Byzantine fault. A lot of literature on it. Okay? But make it practical. You have to reduce the cost you have to pay to implement Byzantine fault tolerance, which is still very high. Okay, so most system designers make a choice saying that's too expensive, can't pay that price. So we won't deal with it. We only deal with crash failures. Okay, so let's talk a little bit about Byzantine fault. So first we'll talk about Byzantine fault of a network, and then we'll talk about Byzantine faults of a node itself, okay, but not that of the network. And so the way these problems have been described in literature are through analogies with military exercises or armies trying to attack one another. Okay? So this is basically referred to as the two-army problem, the first one. Here the scenario is you have two processes, right, that are not faulty, right, but they are communicating over a network that is faulty. So, so we are assuming in this case, this is the simplest form where you are sending 1-bit messages. Okay? Each process is sending a bit to the other message, but the network is Byzantine faulty. Either it can, sometimes it delivers that bit that was sent exactly the way it was sent, sometimes it flips it, and you cannot tell what happened. Okay? And in this case, you want to reach agreement. Okay? You want to know whether the message was actually transmitted successfully. And the way to think about that same problem of two processes communicating over a Byzantine network is the two-army problem. Now, the two army problem is as follows. So you have army that's divided into two. Okay? And there is a general that is actually managing the two armies, and they want to attack a common enemy. And these two generals want to agree on when to attack, or let's say whether to attack. So the message is yes or no. Let's say they're simply trying to say, should we attack or not attack? And the way they will communicate is through a messenger who has to actually traverse from where the first army is located to the second army is located, but through enemy territory. Okay? So we'll assume that since the messenger is going through a hostile territory, anything can happen to the messenger. In particular, the messenger may get captured, and you may say send actually a bad messenger to the other end with the wrong message. Okay? Or the messenger may reach successfully. Okay? So then the question is, how do the two generals know that the message they exchange was actually received successfully, and both of them know what the message is? Okay, that's the question. Is that clear? Okay, so what would you do? Okay, the first thing you would do is you would basically you could send the messenger over, and then how do you know whether the messenger reached the other end or not? How can you figure out? Okay, so you can get an acknowledgement. The messenger takes a message, the other general signs the message or says, yes, I received it, sends the messenger back. Okay? So the messenger, let's take the case where the messenger is not captured at all. Okay? Messenger went to the other side and messenger has come back. Okay? So the first general knows that your message was received successfully, okay, because the message was delivered and the messenger comes back in the case where you did not flip the message. But then how does the second general know that the acknowledgement was received? Okay, so I know that I said, yes, let's attack. Messenger went and messenger came back and said, I delivered the message. So I know that the other side has received the message. But how does that general know that I have received the acknowledgement, so I know that he knows or she knows? Then you send another acknowledgement. Okay? So you'll send an acknowledgement back. Okay? That messenger may reach the other end. Okay? And now that general knows that I know, that they know. But then how does this first one know that the act to the act was received? Okay? Because anything can happen in transit, the message never reached. Okay? So you can keep sending acts to acts, but you are never guaranteed whether the final act was actually received. Okay, so this is basically referred to as what is also called common knowledge. Common knowledge means I know that not only I know something, but everybody else knows something. Okay? So you will basically reach agreement when there is common knowledge, when everybody knows and you know that everybody knows. Okay? So in this case, you may know, but you don't know whether the other party knows something. And if you keep sending acts, you know that they know, but they don't know the reverse. So this is going to continue till infinity, and you will never reach agreement. Okay? So in fact, you can have properties in two perfect processes can never reach agreement in the presence of an unreliable channel. Because the channel can throw away the message, it can flip the message, so I never know what has actually been received as a result of this. Okay. So this problem you cannot solve. Yes, because the channel is not untrustworthy, you cannot actually exchange messages reliably if you don't know if the messages are reaching. Yes, question.
Is it because of just using the bit information? Could be if we had some extra security, like you could send a message that only the other general could read using, say, public cryptography, then could you be sure with, say, the TCP NAC model where you have 3 acknowledgements, 2 acknowledgements?
Okay, so question is, if you could send it encrypted, would that work? Okay, the problem is you don't know what you're sending. So first of all, you could have encrypted it. It doesn't matter because the Byzantine network can do anything. It may decide not to deliver the message at all. Right? Because it's a Byzantine network. Right? So if you're sending a message and the message is encrypted, the enemy can simply capture the messenger and make sure the message is never delivered. That's a possibility. So how do you know the other party has received it? You have to wait for an act. Act could be encrypted as well, but you always have the case where the network decides to drop the message rather than changing. So there is no way to solve this problem, regardless of whether you encrypt it or do something else. Okay. So this is the two general problem with the unreliable network. Okay. So we'll assume this you will not worry about this. because you can't solve it. Now we'll talk about the Byzantine generals problem, where we are not going to worry about the network. We'll assume the network is reliable, but one of the generals is not trustworthy. You have n generals. Okay? They are trying to coordinate an attack on a common enemy, but some generals are untrustworthy. Okay? They are turned into traitors. You don't know who is the traitor. Okay? Nobody knows who is the traitor except that the generals that are traitors themselves. Okay? And you are trying to exchange messages to reach agreement. In this case, the agreement is what time to attack or whether to attack. It doesn't matter what you are trying to reach agreement on, but you want to reach agreement on something where there are untrustworthy generals. Okay? So now you can map this directly into our server case where the generals represent replicas. Some replicas may be spewing garbage. They can do arbitrary malicious things. Okay? Sometimes they may seem to work perfectly well. Sometimes they may just change the message. They can do any arbitrary things. Yet you want the remaining trustworthy replicas to agree on the results of a request. A request came in, all of them processed it, okay, and some untrustworthy replicas may produce garbage, it doesn't matter, yet you want some agreement on what the right response is that you send to the user. Okay. Network is not the problem here. We'll assume the network is reliable. Because the network is not reliable, there is no solution. So we'll assume network is reliable. So how do you isolate those m untrustworthy generals? And yet produce responses. So that's the question. Clear what the question is? Okay. So here is a way, this is called a Byzantine general problem, another of those problems that was actually proposed initially by Leslie Lamport. And this is a way this protocol is going to work. So we will assume in this case that there are 4 generals. Okay. One of them is faulty. We know who is the faulty general here, which is 3. Okay. But the nodes themselves don't know. They have to figure this out on their own. But we do know. Okay. That's why we can observe what's going on. Okay. So here we have the Byzantine general problem for 3 loyal generals and 1 traitor. Okay. We will isolate the traitor and still produce a correct response. Okay. So the way this works is basically you have to ask, you poll everyone, okay, saying what is the response to, let's say request comes in, it's a web server. Doesn't matter, it may be a database server. Request comes in, you process the request to produce a response. Okay, once the response is produced, basically you are going to have this notion of voting, but not real voting. The way you do voting is you ask everyone what response did you produce, okay? And then you compare. Okay? And then we'll do this recursively and we'll see that in 2 rounds we can figure out what the right response is regardless of who the traitor is. So this is the way it's going to work. Okay, so each node is now going to, after it produces a response, ask everyone and say, what was your response? So 1 is going to say, I produced 1. Okay, 1 is my value of the response. Okay? So you basically exchange all these messages. 3 is malicious. So it can send arbitrary things to arbitrary. So when you are asking what is your response, you may send x, which is an arbitrary variable, to 1. You send y to 2 and z to 4. X, Y, and Z could be arbitrary values because it's a Byzantine fault. They could be the same and the right response. You could send the right response to some, the wrong response to another. You could send different responses. It doesn't matter. We don't know and we shouldn't care what X and Y and Z are, and yet we should be able to figure out what the right response is. Okay? So at the end of this process, okay, each has received a correct response from the correct processes and an arbitrary response from the faulty process. Okay? So this is what you got. So 1 has gotten 1 from itself, 2 from 2, 4 from 4. Okay, these are not the values of the responses, these are the responses themselves. Okay, and 2 has gotten 1, 2, y4, 1, 3, 1, 2, 3, 4. 3 can always respond whatever it wants to itself. So let's say it gives the right response to itself. And 1, 2, z4 is what 4 has received. Okay. So now what you do is you basically ask everyone all over again, saying what did everyone else tell you? Not that what was the response you produced, but you ask everyone else, now tell me what you heard from everyone else. Okay? So in this case, 1 is going to send this message to everyone else. Okay? 2 is going to send this message to everyone else. 3 may again send garbage. Okay, so in this case, it's going to send some arbitrary things to arbitrary ones. And 4 is going to send this. Okay? So at the end of round 2, this is what you have received. Okay? So you got 1, 2, y4 in round 1, and then basically you got a, b, c, d from 3. And you got 1, 2, z, 4 from 4. Okay? And then 2 got that and 4 got this. So now if you compare, so you will see that when you tell the truth and other people are telling the truth, you get the same responses. But 3 can cause send arbitrary values, but it gets outvoted at the end of second round because there are 2 others that are disagreeing with 3. Okay, so if you actually see what has happened here, you see that this and this are agreeing, and you can isolate that 3 is sending garbage because it's not, because you can see that 3 said something to 1 and said something else to 4. And the same thing is true here. So you can basically isolate who is lying because that row and that column will actually disagree. Okay, but the others are agreeing here. Okay, is that clear? So basically, you have one now basically it has responses from 3 others. If one of them is lying, the other 2 will agree. Okay, and so then you can figure out that who is lying. And it's okay if 3 decided to send the right results. In that case, there is nothing to worry about. In this case, the 3 may have produced correct result, in which case it will agree. So then the result will still be the same. You want to produce the right output. Okay? Yes.
What if the number of traders is very large in comparison?
Okay. So question is, what if the number of traitors is large as compared to the number of generals? This scenario assumes 1 traitor, 4 generals. Okay, we will see the actual result is if you have m faulty generals or m traitors, you need 3 plus 1 m total nodes for this protocol to work. Same protocol is going to work. You can plug in whatever value of m you want. If you want to deal with 2 traitors, then you will need 7 such processes. Okay? They will all do the same thing. Okay? The 2 traitors will send garbage, but then the others will override. This is showing a scenario where m is set to 1. Okay, so that's why there are 4. Okay, so this should tell you that if you had fail-stop failures, if you had 1 faulty process, you needed 2 replicas. If you have Byzantine failures, if you have 1 faulty process, you need 4 replicas. You will vastly increase the cost to actually deal with Byzantine faults. Okay, next question.
So what if the trader sends consistently false data?
Yes.
Would it be able to detect the?
So what if you can analyze this any way you want. Let's say first case is traitor actually sends the right response and sends the right response to everyone. So all of these values are going to agree because everybody is producing the same response to the request. No problem. Okay. What if the traitor sends an incorrect response but sends the same incorrect response to everyone? Okay. So then what would happen is this column is going to agree. It's the same thing. But that is going to disagree with what the other 3 are saying is the response to this request. So I'm outvoted anyway. Okay, I say what is 1 plus 1? Traitor says 4, everyone else says 2. Okay, and if 3 out of 4 are saying that is 2 and the traitor is saying something wrong, is inconsistently saying wrong, it's still outvoted. Okay, and it could send different responses to question 1 plus 1 and you'll still get outvoted because you can see that that node is sending garbage in this case and sending different wrong values to different. How do you come up with the number of traitors? Okay, so this is a different problem. So you are asking how do you decide how many faults can occur in the system? So that is clearly not known ahead of time. You have to design the system to tolerate m concurrent faults. If you have more than m faults, the system will stop. Okay? Just as if you have crash fault tolerance and you put 2 replicas, you can deal with 1 fault. You say what happens if both fail? Nothing much can happen. System goes down. So if you design this with 1, but 2 of them turn Byzantine faulty, this will not work. It will produce wrong responses because it's not designed to work for more than 1 concurrent point.
Is there a way to detect the number of traitors exceed
Is there a way to detect number of traitors? So you
n?
can't actually detect that. You have to decide this ahead of time and then vote based on how. Pick the value of number of faults you can encounter in your system. Based on that, you decide. Now, all these are right questions in that you cannot a priori predict what the fault could be. Right? The fault could be a software vulnerability that some hacker has actually maliciously taken over that machine and it's producing garbage. If the same software vulnerability exists in all of those, you will have more than some number of faults. The faults could be as a result of anything. Right? Real bug. Some sort of machine got taken over, hacker is producing garbage. Yes, question.
Is there an intuition as to why 3m plus 1 is a minimally required?
Yes. So I'm going to show you the question, why is it 3m plus 1? We'll do the same thing from one faulty process and reduce it, okay, from 4 to 3 nodes. Okay. And now you will repeat this and you see what happens. So in this case, 3 is still faulty, 1 and 2 are not. So 1 is going to send 1 to other nodes, 2 is going to send 2, 3 is going to send x and y. Okay. So here you will basically see that this is what you received at the end of round 1. 1 to x, 1 to y, 1 to 3. Okay, you repeat again. Okay. Then you got 1 to y, a, b, c, 1 to x, d, e, f. Okay. So now what has happened at the end of round 2 is you know that the nodes are not agreeing on the value. Okay. Because you know that this and this is not agreeing here. Okay. But you don't know who is right. So you can't isolate the traitor. You know that there is a traitor, that somebody is producing garbage, but I can't tell who. Okay? So that's the intuition. I can sort of, if you think about it from a person's perspective, let's say you have 2 friends. You ask them a question. They give you different responses. Okay, you know one of them is lying, but just based on the response, you don't know who is lying. That's the right? So if you have 3 friends, you ask them the question, and only one of them is lying, the other 2 will outward the liar. So you can not only can isolate the liar, you know what the right response. So if you have less than 3m plus 1, in this case it is actually 2m plus 1, you can actually figure out that there is no agreement, but you don't know what the right response is. That's the problem that you're trying to deal with. Yes.
You have some knowledge as well, right? Why don't you use your knowledge to cross-verify the responses to make sure?
Okay. Question is, why can you not use your knowledge? We will come back to that. In fact, when the way these protocols are actually designed is, in the number of replicas you can do away with this 3m plus 1. You can only do 2m plus 1 in the replica because of that observation you made. Okay. But when you want agreement, you need 3m plus 1. It's a slightly subtle point that you're raising, saying, if I know I am doing the right thing, why should I not figure out what the right response is? Okay? But you remember that you are a software processor. You don't know if you have a bug or don't have a bug in reality. You may get outvoted yourself. Okay? So you have to deal with the same problem as what you had here, which is there is a computation and there's a voting phase. Okay? In this case, the Byzantine general problem, we combined the two. The generals not only produce the answer, they vote. If you separate it, you can do what you said, which is reduce the overhead here but not here. That's a subtle point. I don't want to go into the details here, but that observation has actually been used to reduce some of the overheads here. So it's not always 3m plus 1. Only the voters need to be 3m plus 1 because you don't know which voter may have failed. Okay. Any other questions? Okay. So this should make it clear why the Byzantine general problem requires 3m plus 1. Okay. If you do this, you can actually deal with Byzantine faults. I mean, do this meaning do 3m plus 1, not 2m plus 1. Okay. But the cost is very high in most of the systems. As a result, no real system has actually paid the price of having 4 replicas and have voting and so on and so on. It's far too expensive. Okay. So crash faults are actually the way to go. Okay, so going back to that question that you raised here, so that property is actually stated here. So m faulty process, okay, agreement is possible if 2m plus 1 process function correctly, okay, and then you have 3m plus 1 voters. Okay, that's a property, as I said, we won't go into. And this observation was made back in the 80s, incidentally, which is 30 years ago. But still, there are no cheap ways to implement Byzantine fault tolerance. Okay, this is an area of research. You still see papers appearing saying cheap fault tolerance or doing this on the cheap for some special cases. Okay. So Byzantine faults, the takeaway message is 2/3 majority, not strict majority, is 2/3 majority. That's what 3m plus 1 gives you. Okay. So what this technique should also tell you is just to detect a fault, you just need 2k plus 1, which is basically, I know I have 2 friends, one of them is lying. That's much easier problem. But to detect a fault and get agreement, need 2/3 majority. Okay, that's why you need 3m plus 1 to isolate the liar and find the right response. Okay, so this whole notion of agreement is an interesting question. We'll keep coming back to this. So when we talk about distributed commit next time as well as Paxos, these are all protocols designed to reach agreement. Okay? They make different assumptions about what kinds of faults can occur. Okay? By default, Paxos doesn't assume Byzantine faults. Okay? So the standard version of Paxos is much cheaper. If you have Paxos in the presence of Byzantine faults, you may need something like this to reach agreement. Okay, you need this voting and voters and so on, and they are far more expensive to deal with than straightforward Paxos, which we'll come back to. Okay. So to get cheaper versions of Byzantine fault, there are different models. Okay, what kinds of faults exist. So the most complex one is Byzantine. Okay, but there are other kinds of models where there are collaborative faults, or some nodes collaborate, but other nodes cannot be trusted. Or you can have some trusted nodes and other less trusted nodes, and you basically try to exploit these properties to somehow reduce the cost. So there has been all these flavors of how to reduce the cost of dealing with Byzantine faults that people have looked at. But again, if I'll put up some papers on some of this if you're interested, just as out of curiosity. But as far as the book and the course is concerned, this is all we will talk about as far as Byzantine generals problem is concerned. Okay. Go back and read the original Byzantine generals problem paper. It's an interesting one. It's written back in the 80s where this problem was first proposed. Okay, so I have a few minutes left. I'm going to talk a little bit about communication technique. I had talked about this back when we did RPCs, if you remember. We said if you have RPC requests, what happens when either the server fails or the network fails and things like that. So putting that in the context here, as you can imagine, all of that discussion assumed that it was crash failures. Either the network simply dropped a packet, server simply crashed and failed to produce a response. Okay. If you had Byzantine fault, none of that would work. You got a response, but you don't know whether to trust it because the server produced garbage. So that's something to keep in mind. We did talk about all of these possibilities. This is just a reminder to go back and review that material from the RPC lecture, which was actually from this chapter. I just brought it up earlier. Okay. Now here is a way to achieve reliability in most networking scenarios when you have packets that get dropped. Okay, as was pointed out earlier, the way to do this is you assume that there are acknowledgements coming back. Okay? But we are not assuming that processes are Byzantine faulty. This is why you don't need to keep sending ACKs for ACKs and things like that. So in TCP, you send a packet, you get an acknowledgement, you know the packet has been received. You don't actually send an ACK to the ACK or anything like that because we don't assume that the network is Byzantine faulty. Assume that it either drops a packet or delivers it right. Okay. Same is true when you do multicast. Okay. What this slide is showing is how do you deal with failures of the network failing to deliver packets when you have multicast message. So in multicast you have one sender and many recipients. Okay. So this is group communication. So sender sends a packet out. Okay. This packet actually goes to many different recipients. Okay. So there may be n recipients. So now assume that if you did whatever TCP did, was whenever a recipient receives a packet, you send an ACK back to the sender. Okay. So if you have n recipients, for every packet that goes out, you will get n ACKs back. If some nodes don't send an ACK, then we'll time out and retransmit to those nodes alone. But the problem gets worse as the number of recipients keeps increasing. What if there are 10,000 recipients? Okay. Every outgoing packet means I get 10,000 packets back. Okay. What if there are 50,000? If you send one packet out, you get 50,000 ACKs. Okay. So sending acknowledgements is a good way to ensure that your packets reach. And if they don't reach, you retransmit. But this doesn't actually scale in the case of multicast, simply because the overhead of dealing with acknowledgement will far outweigh the overhead of sending the packet itself as the number of recipients grow. Okay. So then the question is, if you want to do reliable multicast and you think that the cost of sending ACKs is just too high, how do you deal with packets getting dropped by the network? Okay, you send a packet, Some subset of the recipients got it, others did not. How do you detect that if you don't want to pay the price of having everyone send individual acts? Is the question clear, first of all? Okay, we are talking about a network, okay, simply dropping packets. TCP simply uses an ACK-based scheme. And I was asking your multicast where if you just use an ACK-based scheme, the overhead is too high. How would you deal with this problem?
You could, I mean, the diagram you draw is like hierarchical structure. So you could use a hierarchy of acts back.
Okay.
So that you collated the root of each.
Okay, so you send a hierarchy of acts back. Okay, so let's say, and then you are saying let's collate the acts and send one act up. Let's say this node here did not receive the packet. Okay. Act came back this way. Okay. No act is going to come from here. Okay, so what will this node send up? Collating.
Nothing. We're going to retransmit that path here.
Yeah, like what he's saying is just retransmit it from that parent node.
Okay, so
Wait for an act.
what did you say? Retransmit from this node?
Yeah.
So you are saying you can do intermediate buffering. Let's assume that you don't do intermediate buffering. Like TCP is end-to-end. Right? You could of course cache the packets in between and then retransmit from between. Okay. So what you said is sort of right in that what you can do is rather than sending an ACK, you can send what is called a NAT, which is a negative acknowledgement. Okay, you just flip what you said around. Rather than doing aggregation, if you receive successfully a packet, don't send anything back. If you don't receive it, complain. Send a negative acknowledgement I did not receive a packet. Okay? And so if you do NAC-based schemes that are much more scalable when you have lots of receivers than ACK-based scheme. Your question.
So how does it know it was supposed to receive a packet?
Okay, that's a good question. That was going to be my next question. So how do you know that you have not received a packet in order for you to send a negative acknowledgement? Okay, to complain, you need to know that you missed something to begin. Okay, if I don't receive anything, should I assume the sender is silent or I'm not receiving packets?
I guess the assumption is you will eventually receive a packet with some sequence number being so high that you realize that you missed a lot of things.
Okay. So what you said is right. So the way you figure out, it's a very good question. The way you figure out is you have not received anything. You will say just as TCP sends packets with sequence numbers, in TCP everything is a sequence number. Okay, you will assume that packets are numbered. Okay. So if you received packet 5, 6, 7 and then you did not receive 8 and you received 9, you know that something is missing because I received the packet after the one I was supposed to receive. Then you send a negative acknowledgement saying, wait a minute, I did not receive 8. So you send a NAC for 8 and ask the sender to send it back. Right. So this only works so long as the packet you have not received is the last packet that was being sent by the sender. And the way you detect the last packet is just as in TCP, you have a fin saying I'm done with transmission. If you receive a fin, then you know that the last packet has not been received. Okay. So this is basically how you deal with lost packets in multicasting. Unicast use acknowledgements, in multicast use negative acknowledgements, but deal with the problem of how do you know a packet is missing by using sequence number, and if you see a gap in between, then you send a NAC saying I did not receive this, please retransmit. And that is where some of the suggestions that were made come into the picture. If you have intermediate buffering, the NAC doesn't have to traverse all the way back. Okay, you can actually retransmit from the most recent node of the hierarchy that still has a copy of the packet. Okay, typically if these are routers, they're not going to actually buffer any packets. They don't have the memory capacity to buffer. But if this is an overlay network, you may actually have intermediate buffering. Okay. So this depends on whether this is an IP level multicast scheme or an application level multicast scheme, in which case you may actually have buffering. So this is something to keep in mind of how networks deal with packets that are dropped over the network. Byzantine, the packet delivery can't deal with. Okay? Simple dropping of packets you can actually handle, and this is the way either TCP or IP multicast or application level multicast would deal with these issues. Okay? So we'll stop here for today. Next time I'm going to talk about distributed commit, and maybe towards the end we may start talking about paxos and things like that.